Hello and welcome to this video about solving multiple equations. Is it possible to write a computer program that could solve a group of equations like this, substituting these known values in and getting values for these unknown variables? Well, I've done it and I'll show you how to do it. Well, firstly I'll show you how to solve any equation like this for any variable in it without using any algebra. The first step is to write out the equation and its unknown variable like this. Then we have to get this equation into a form so that one of the sides is equal to 0, like this. We then make this form of equation into a function called f, and then eventually solve for f equals 0. So as to find u. We then substitute values into u of 0, 1, 2, 3, etc. to get the corresponding values of the function f, and try to construct various functions from these, like the linear function f is equal to c plus du. This requires only two values, f0 and f1, to do it. And then we can use the remaining values like f2, f3, etc. to check if it really is a linear function. Only a few extra points are needed to find out if it is. The next step then is to solve this equation fu is equal to 0 using this linear function that we found. There's a compact formula for it here. Then this solution must be checked, so this value of u must be substituted into f to verify that it really is a solution. Then if f isn't linear, then try to use other types of equation, like quadratic equations and exponential equations and so on, and then try to solve u for these. Then to quickly go over this again as a second summary, if we have a function fu, then we get lots of ordered pairs from it, like 0, f0, 1, f1, 2, f2, and we then reconstruct the function from these points, and then to check that this function is right using these points that we didn't use to reconstruct the function, and then to solve for this function fu is equal to 0 using the reconstructed function. So taking our first example, we need to solve this equation for these knowns and unknowns. This is one of the equations of motion for constant acceleration. This is how a human would do it. He or she would substitute all the known values in, leaving the unknown values unsubstituted. U is left as u, and this expression would be continuously simplified until a value for u is found, which is the solution, and units are added at the end, and since u is a velocity, they are in meters per second. This requires some symbol manipulation and therefore some algebra. A computer could not so easily do this, but it could manipulate the expression in another way, so as to solve it without using any symbol manipulation. The first step is to write out this function as an expression that is equal to 0, called equation 2. The next step is to set this expression equal to a function called f, so that u is a solution when f is equal to 0. This is equation 3. It looks a bit like writing the same thing differently, but it makes a real difference, so that the equation can be solved in a different way. The next step is to substitute all the known values into this equation, and substitute u is equal to 0 for the unknown variable we're trying to find. And so we find the value of f corresponding to u is equal to 0, which we'll call f subscript 0. Similarly, we substitute all the known variables into this equation as well, but this time setting u is equal to 1, So this value of f corresponds to u is equal to 1. We'll call this value of f subscript 1. So now we have to reconstruct the function f from f0 and f1 to look like this linear equation with variables c and d. C is easily found to be f0 since it is the constant value of the function, and the term du is equal to 0 when u is equal to 0. So this is the value of c. So it was very convenient to find f0. C is also equal to the f-intercept where it crosses the f-axis. D is equal to the slope of the line and is given by this equation. And so it simplifies to this. So it was also very convenient to find f1 using u is equal to 1. And so this is the value of d. Don't worry too much about subtracting negative numbers because computers don't get confused by it. And so here is our reconstructed linear equation, but we need to check if it is correct, that is, if it is true for every point. But first we can solve it, and to do this we need to set f equal to 0 so as to find u. We substitute in this reconstructed linear equation to stand in for fu. Then we solve for u, giving us this value for u. We can try to find a more general solution to this equation. We firstly start with this linear equation we've found. We then get a value for u in terms of this equation. We then substitute the values of f0 and f1 into it. We then get this general formula for the solution that we can use to get the solution much more quickly. We can use a graph of this equation to see what f looks like in terms of the unknown variable u. Here are the 2 points 0, f0 and 1, f1 on the line. And here is the solution u, 0 that we're trying to find. And the line represents what f would be for every possible value of u. We could use the point 2, f2 to check whether or not the function is correct for one other point. So if it is, then the function is highly likely to be correct. We could even use another point like 3, f3 to check it again. It looks correct for 3, f3, so it is even more highly likely to be correct. Remember that computers don't manipulate symbols like we do, so they need to use these mechanical methods to check for linearity. Here's an example of a function, fu, that goes through 3 of these points and could pass as being a linear function when it isn't. But it would fail the test for a second checkpoint. It is highly unlikely that such a function would manifest itself in the equations of motion. They never get to being more than quadratic. And now to check this function analytically. We'll use the point 2, f2 to check this function. Firstly, we'll calculate f2 from the reconstructed linear function. We'll substitute all of the values into it, and we'll get this answer for f2. Then we'll calculate f2 from the original function, equation 3. We'll substitute all of the values in, this time using the motion variables a, t and s instead of c and d. And so we get the same answer. So this function is more likely to be linear. And lastly, we have to check the solution we just found by substituting it into the original function f. And here it is. And substituting all of the values into it gives us this expression, which is equal to 0. So u is equal to 5 is the solution. So what about for a case where the function isn't linear, like, for example, a quadratic equation? In this example, we have to find a solution for t. and a term for t squared appears. So f would be a quadratic function of t. So we manipulate this equation to be a function of f, like we did before. And we substitute t is equal to 0 into it to find f0. And so after substituting all of the values into it, including t is equal to 0, we get this expression, which will give us this value of f0. And we can similarly find f1. And since ft is quadratic, we need f2 as well. We need a total of 3 points, or 3 ordered pairs. And so we have to find the polynomial coefficients of ft, which are c, d and e. This is what the values of f are in terms of these coefficients. And we can find c, d and e in terms of these values of f by using matrix techniques, which I won't show here, but that's how it's done. In any polynomial, c is always equal to f0. And after substituting these values of f into these equations, we get these expressions. And so these are the coefficients of the polynomial we're looking for. And so this is the reconstructed quadratic function ft. And here is what this function looks like when plotted as a graph. Here is a function that can pass through all 3 points that we've just used to find the quadratic function, plus a checking point, but not the second checking point. So there are functions that can trick the computer into thinking that it's quadratic when it's not. I had to use a lot of computer power to find it though. We're now going to check that the function ft is really quadratic by checking it with another point or ordered pair, 3, f3. Here we're finding f3 after substituting all of the values into the reconstructed quadratic function. And so we get the first value for f3, and we'll use the original function to find the other value of f3. And so we'll substitute all of the known variables of motion into it, and we get a second value of f3. The two values are equal, so it seems to be quadratic for this point. We can similarly check it for another point, 4, f4. Here is its value as calculated from the quadratic function, and here is its value from the original function. So these two values are equal, and thus the function is even more highly likely to be quadratic. And now to solve this quadratic function f for t. We write down the function we'll be using to solve it. We'll set it equal to 0. And these are the two values for t using the quadratic equation formula. And then we substitute the values for c, d and e into this formula. And so here are the two solutions for t. I should round the second one, but I wanted to show it to you as it would be newly calculated in a computer. The rounding can be done later. Now to check these solutions. We firstly try t is equal to 5. So substituting all the values in gives us this expression, which gives us this answer, 0. So this is a solution. And similarly, the other solution is correct too. Now let's try out a black box model of this equation, so that we can see it from the computer's perspective. We can't see what the function f is, and only see its outputs for different values of the unknowns, just like the computer sees it, so that it has to reconstruct the function. We'll let s be the unknown variable. So we'll let s equal 0 so as to get f0, and then set s equals 1 to get f1. Then we'll try to match it to a linear function as shown. This is the value of the constant, and this is the coefficient of s, or the slope of the line. We'll check it for the point 2, f2. So both versions of f2 are equal, so the function is correct in this case. And both versions of f3 are equal to, so the function is correct again, and we may assume f to be linear. And now to solve the function, that is, to find s when f of s is equal to 0. And the solution is given by this compact formula that we found earlier. And substituting all the values in gives us this answer for s, so this is the solution. And now we check the solution to see if the original equation gave us 0, and it did in this case, so the solution is correct. It may not have given us a solution in some very rare cases. And now to have a sneak preview of how I use this method to solve equations in a multi-equation solving program. Here I've got all the variables stored in an array, and I can set variables with the correct symbolic names equal to them, so that I can substitute them into equations without making mistakes. VAV is equal to average velocity. I've also got all of the equations numbered, so I can more easily control access to them using loops and if statements. I can set I3 to loop from 0 to 5 until it finds an equation it can use to find an unknown variable, and then find it and tick it off as being found. Here is a place in the program where I call this function and substitute 1 and 0 into them so as to eventually find the constants c and d and solve the equation. I've written it in JavaScript, so I wouldn't write the code as nicely as I would in C. I'd just return function values through another variable rather than through the function. Here is a place in the program where I can check about 20 points to see if it is correct. I could have just as easily checked 1,000. A huge amount of checking points could slow the program down, but 20 seems to be a good amount. So that's it for now. I'm going to make another video later to show you how to put it all together. I hope that this has been helpful to you so far.